Yes.
How many have been to NASA before? Other centers, or just Goddard, or all across the agency? Learning a lot? Good. My name is Brian Roberts. I work here in the Satellite Servicing Projects Division. My background's in robotics, so I will be more heavily focused on robotics. I will warn you, I'm not a laser person. I didn't stay to Holiday Express last night, so I know a little bit about lasers. I'll try to answer your questions as best I can, but more heavily involved in robotics. If you have questions, certainly let me know. So our group at Goddard, a lot of the folks I work with came from the Hubble Telescope Servicing Group. Our group at Goddard, in fact, the clean room, I don't know if you saw the clean room kind of behind us here, all the instruments that flew to Hubble went through there. Our group helped manage, along with other colleagues at NASA, all the servicing missions to Hubble. Great experience doing that with the astronauts and building tools and all the great stuff on orbit with the shuttle. We then transitioned the group into doing robotic servicing. There was temporarily a year when the Columbia disaster happened and NASA was debating what to do with Hubble. We did at Goddard look at robotically servicing Hubble because we had some hardware on the ground ready to go, and we looked at working on that for a while. And then they switched back to shuttle mission. And once they stopped flying shuttles, we were asked to look at robotic servicing. So the room you're in now, we call the ROC, or the Robotics Operations Center. It's where we prove out all the technologies needed to go up and service satellites. So when you all get on the bus today and you go in your cars and you drive home and you notice the fuel's low in your car, what are you going to do? What do? You go to the gas station, right? Do you know what we do with satellites when the gas gauge gets low? We throw them away, which is great if you build satellites. It's not great if you pay taxes like I do, and I assume you all do, and we have to pay for those satellites to get replaced. We're trying to change that paradigm. So what we're trying to do here in our group at Goddard is to show, because no one's ever done that, satellites weren't designed to do that. In fact, most satellites weren't even designed to be serviced. Hubble's one exception. The space station's designed to be serviced. There are a few others that were designed in the early days of the shuttle program to be serviced, but the majority of satellites, the paradigm is you build a satellite, you insure it. So if during launch the satellite doesn't get where it needs to go, you're the insurance provider, you pay him to build you a new satellite, and it's great, and it's wonderful, and the market's set up to do that. But that satellite's up there still just needs to go in the right spot. So same thing, if you parked in the wrong parking spot, you don't say, oh, I guess I'm gonna go buy a new car, and I'll park in the right spot, right? What do? You move the car to the right spot. So if you had a robot or a servicer or a tow truck in orbit that can grab a satellite that was in the wrong spot, put it in the right spot, maybe you don't have to pay the insurance company, maybe you don't have to build a new satellite. So that's some of the paradigm we're trying to change. In addition, if the satellite runs out of fuel, collecting great science, maybe the replacement satellite isn't ready yet. So what happens is scientists just don't get data for the time it takes to launch a new satellite. So we're trying to change all that by maturing the technology. But because it's challenging, people haven't done it before, it hasn't been designed to do that, we need to prove it out here on the ground. And that's what we do here in our facility. So what you see in front of us is an example of how to do that. Because much like the early communication satellites, we feel NASA and the government really has to take that risk. Because it's not in the marketplace, it's not really up to companies now to decide to just go start a business. They really you need to prove you can do that. And that's, we feel the government's job is to take the risks for the taxpayers, for everyone, and then hopefully the commercial industry says, oh great, they approved the risk, we're going to now go do that. So what we're going to do is go up and we want to service a satellite. In this case it happened to be Landsat 7, which again wasn't designed to be serviced. And the idea is eventually Landsat's going to run out of fuel. We've got Landsat 9 on the ground ready to be launched, eventually to backfill for it. So eventually Landsat 7 is going to come out of its orbit. Landsat 9 is going to go up and collect some data. So it's a great thing to go up and service, because if you don't quite get everything done right with the satellite, and another one's on the way, you're not taking a huge risk. So the idea is, if you look at the bottom right portion, right down here is where the fuel valves are to put fuel in it. We have to go up and get to those. But before we do that, this satellite's floating in space. It's going around near the poles. It's a couple hundred miles up there, going 17,000 miles around. The first thing you need to do is launch something up to go rendezvous with it. So if you look at the silver thing on the bottom, basically what this is another satellite. If you see the picture here, essentially what we're going to do is take a satellite. On the top of that satellite bolt what we call a payload deck that has tools, robot arms, rendezvous sensors, including lasers, everything you need to go service the satellite, the fuel, the hose, all that sort of stuff. And you fly that satellite to find the other satellite. So from very, very, very far away, many kilometers, you look and you say, oh, Landsat 7's over there. It's just a big shiny thing, looks like a star. Then as you start getting closer, you start using lasers to bounce off the back, all this shiny MLI, you start bouncing and saying, oh, it's 10 kilometers away. Now I can start to get closer. Then you get a little closer using other lasers and visual sensors, you start to say, oh, okay, I see how it's moving. It's tumbling, or it's moving this way. Now I can, like with an ice skater, or like the relay race, you don't just kind of go up, right, as they're running by, don't just stand here and grab the baton, you catch up to the person, right, you watch when they do the races. Same thing here, you have to catch up to that, because this thing's going so fast, if you just launch straight up from the ground, it's going to go past way too fast. So you kind of get in the same orbit, you kind of chase up behind it. So you use lasers to determine first where it is, what direction it is, how far away it is, then kind of what rate it's moving at, so you can then fire thrusters and control algorithms on the servicer spacecraft to know how to kind of match it. So if you were standing on the payload deck here, looking at Landsat, if you had it perfectly matched, it would look like Landsat wasn't moving. If you ever watch a spacewalk, right, the astronauts aren't all flailing around, right, because they're kind of moving the same rate as the space station is around the Earth. Same thing here is that you want the servicer to kind of be moving the same rate, so it looks like it's not moving, then it's easy for the rover to reach out and grab it. So the challenge is to do all that, because no one's ever really done that. Usually when we do rendezvous like on space station, there's features on the space station tell you where they are, or you're sending a signal. You're the spacecraft. Here's where I am. Here's, you're providing supplies. I can tell you where I am, how far away I am. That's much easier than just I'm kind of bounce lasers and trying to figure out where I am. So we want to buy that risk down. So that's very challenging. The other challenge is these arms aren't very, very long, so they need to reach out and grab the satellites. You need to get really close. And the challenge is, and we find this in engineering, you might find it in your fields as well, Murphy's Law applies all over the place, usually where you don't want it. So to get really close, you need really good accuracy of where that thing is. Well, the prediction of where that thing is off a little bit. So the closer you get, if you're off by a little bit, you can start bouncing into the, so you need to be far enough away that your error in predicting where the thing is isn't going to cause you to break something, but you need the arms to be long enough to reach out and grab it. The other Murphy challenge is if I have video come from the ground. If you look on the wall there, you see those are live views from space right now. But what you see in the view is what happened about a second ago in space. Because it takes the video that long to go down the space station, into the computer, get sent to satellite, go down to the ground, get processed, get transferred to line, and displayed on the screen here. When I have a camera on the end of the robot looking at the ring, I'm standing on the servicer looking out at Landsat, what I see on the screen on the ground happened 4 seconds to 6 seconds ago. So if I use a joystick on the ground to grab it, where am I going to grab? Where Landsat was 6 seconds ago, and I miss it. It's going to be really hard. I can't really try to predict, well, here's where it was, and try to do a fancy algorithm. So the grapple phase is all autonomous. So very tricky. You've got a very expensive, hundreds of millions of dollars satellite, hundreds of millions of dollars servicer, a little bit of error in where I am, time delay. I mean, it's a perfect storm that make all that work. The arm needs to reach out and grab it. So there's cameras at the end of the arm. You can see out at the end here. So those cameras, in addition to their sensors on the payload deck itself, the lasers, the cameras, telling me where the back of the satellite is. And because it doesn't have features, because it wasn't designed to be rendezvous with, what I'm looking at is the one fortunate thing where Murphy didn't get us, is that satellite needed to get launched into space. So if you look on the bottom, you can see this ring down here. That ring is what attached this satellite to the rocket. Most of the satellite, because when you're launching, in this case, science, you want to put as much science up there. You don't want big, strong structures on the side, a lot of metal, because if the spacecraft's really heavy, it's less fuel and less instruments and less science I can do. So most of the satellite you can see is very flimsy insulation. In fact, there's some satellites, if you put back the insulation, there's nothing there but a wire to keep the insulation in place. Because they try to make the spacecraft structure as light as you can. That means there's very few places I can grab onto, because if I grab here and there's nothing behind it, I'm going to go right through the insulation. The one place I can grab is that ring on the bottom is the thing that took all the launch loads, right? If you ever watch a rocket launch, very violent. Where the shuttle was pretty good, about 3 Gs or so, right? Everyone felt about 3 times heavier. The rocket's ease right on, you can pull up to 10 or 12 Gs. Very violent, moving around. So that ring really held on really tight. So fortunate is that's a really good place to grab onto. So that's what the robot, both the servicer down here will use lasers and cameras to look at the ring and say, the ring's there, it's this far away, and it's oriented this way. Tells the robot to kind of reach out and go and get it, but because that's not quite precise and the robot arm gets in the way of the sensors, there's also cameras at the end. The cameras in the arm, which are much closer to the ring, are saying, no, the ring's actually quite a little bit here, and it's adjusting the end of the arm to reach out and grab the satellite. And then it grabs onto it, and it brings it into these berthing posts. You can see these 3 posts here, these silver posts, sets it down, and then this is the configuration to go work on. So it's like working on your car, right? You don't work on your car while it's, I hope you don't, while it's driving down the street. Right, you're taking the mechanic, they put on a lift, they lift it up. This is the lift to get the satellite so the arms can now work on it. So it frees up both arms to go work on it. It means I can go get tools. It also means when this thing's floating in space and I touch it, what's going to happen to it? go away from me, right? Just like on the ice. If we're all ice skating and I come up, as I do with my daughters, right, and they grab my hand, all of a sudden they start going the other way. Same thing in the satellite, it's gonna start floating away. So this also allows us, when we're docked in there, when I go touch this side here to go work on the valves, it doesn't float away from me. So it means I don't have to hold on to it with my arm. I also don't set up this weird thing where I hold on to it and touch it somewhere else. This allows me to work on my car here at the end of the robots. And so what we're going to do is what you would see at the bottom here. The other fortunate thing that Murphy didn't get us is, imagine this on the launch pad. The rocket's down here. A couple days before launch, a technician, because when you build a satellite, there's no fuel in it, because the satellite fuel is very toxic. Right, one drop of that in this room, we're all not in a good place. So they go out a couple days before launch in the nice hazmat suits, and they put fuel in this. But they also want to be able, in case they have to delay the launch or have to get the fuel out, to drain it. So the good thing is the fill and drain valves we put fuel in tends to be on the bottom of the spacecraft, which is cool because I can grab and work around the same place I need to work. It would really, really bad if these were way up here, because then I have to grab down here, I reposition, I have a really long arm. So that's one fortunate thing, that most places we put fuel in the satellite tend to be on the ground. Also means I don't need as much scaffolding when I'm getting to the spacecraft. So that's the work site, which is really close to where I'm holding on to, which is good. But this is what it looks like. For those of you that are probably see a little bit closer there as well. Here's what the valves look like when they're empty. Basically just a valve with a nut on it. So the technician comes and puts a hose on here, closes this up, puts fuel in it first, closes it up. They put a wire in it, because during launch, if this nut opens up and the fuel leaks out, bad day, you get on orbit, you don't have any fuel, you can't continue your mission. So we wire that shut. We put another cap over it, we wire it shut. Because we're really paranoid, we put another cap over, wire that cap shut. Then we put insulation over it, and we tape it down. It's almost like we purposely try not to get back and do anything. So what the robot needs to do is undo everything I just said. It needs to come in, once we've run it, like that's not challenging enough. You need to grab this thing that's moving at, how many thousands of miles, tens of thousands of miles, berth it in there, come in with the tool, cut the tape away. What's this gonna do in space? Probably the place you don't want it to be, so you're gonna have to fold it out of the way, so you need another tool to hold it out of the way. Then you have to go in and cut these wires. So the good thing is the wires are attached in two spots. When I cut it, they don't float away. Because floating away would be bad, because this is going to be running at the same velocity I am. An hour and a half later, it's going to come whizzing by me, and hopefully it doesn't come in the wrong spot and damage something. So it's good that it stays stationary. I remove this cap with the tool. And what happens when I remove this and do that? What's it going to do in space? It's also going to be a projectile coming back around. Thank you. So what we have to do is have the tool hold on to this and then stow it back so it doesn't float away. We have to cut another wire here, remove that cap so it doesn't float away. Finally cut this wire, hook a hose up to it, pump fluid across it, and then fortunately we don't have to redo everything. We can basically kind of put a cap over that's a little bit friendlier. And we did that in Hubble. If you ever watched the 3D IMAX film, the last Hubble mission where they removed all those fasteners, you watch when they close the instrument back out, they didn't put all the fasteners back, right? They designed something that was easy for the astronauts to put a latch in and do it real quickly. Same thing here. We have something that can kind of go in and cover these up and thermally control it, because this insulation is to keeping the valves warm or cold. If these get too cold, the fuel can freeze. If it gets too hot, it can boil off. So you want to kind of protect it. You can put a nice little umbrella over this, much friendlier for a robot to do it. But that's all the tasks the robot needs to do when it finishes its mission. So part of what we're doing is proving that that is not impossible to do. So hopefully in the future, satellite industries and other folks do that. The other thing we're trying to prove is there are other ways to do that to make it easier in the future. So one thing we're demonstrating in this mission is a different way to put a fill and drain valve, which looks like this, which is much easier to plug into. So easier on the ground. It has all the same seals you have up here, easier for a tool to get in there. But also you notice here, it's got Velcro, much easier than tape. Also has a little flap, right? It's little things you think, oh, it's no big deal, but try grabbing this little robot in space. Where do I grab it? I slip out. This is really nice. And the other thing, this is cheating. You're all U.S. citizens, right? You know this secret? Magnets. Stays in place. This doesn't have magnets, so I got to add a tool just to keep this out of place. So we're also trying to demonstrate by doing this mission, what are some ways you can do very small changes, right? When the technicians close this out, instead of taping it, or tape it a certain way, add Velcro instead. We're trying to influence the way satellites are built in the future, because no one's going to come in, we ask this all the time, no one's going to come in, like go into Toyota and say, why don't you change the way you build cars? We've been doing it that way, or GM's been doing it that way forever. We're not. The manufacturers are set up all the assembly lines. You're not going to change the way satellites are built, but you can do these small little things. And the biggest thing, and it sounds silly, is take pictures before you close this out. They don't take, because no one ever has to open this up, right? The technician just says, like, tape this, check, I'm done, but we care. For example, there's a ground wire here. Where's the ground wire? Does it run this way? Does it run that way? Which way did you tape it? And they think we ask them, what's it matter? Well, it matters where the seam is because it's easier to cut one way or the other. So those are things you can do. You don't have to change anything just by taking a picture. But by doing this on the ground, we can figure out what we need to do to figure all this out. Yep.
How does the shift toward like CubeSats change the paradigm?
So very good question. Shift towards CubeSat was the question. So one way is you won't have to service because these satellites are designed to be up there for many, 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 many years. So in some cases, CubeSat you wouldn't service because you wouldn't launch a $500 million servicer to go grab a $10,000 CubeSat. But I think you'll always have, as CubeSat missions get longer and longer, you may eventually need to service those constellations. The other thing with these is there's only certain science you can only get with these sorts of missions. So you're always going to have a need for large things in space.
And then follow-up question. Sorry.
No.
If they did launch a constellation of CubeSats, like prior to that video of like India launching 120 satellites in one go, like could they just, once this technology matures, could they just send with a fleet of that to just one of the satellites via?
Yes. Yeah. Very good question. So we're actually trying to do that. So the challenge is, for example, where the space station is. So the space station is kind of at what we call a 51.5 degree inclination versus the equator 0. Space station is 51. Hubble's 20.5. You can't go to Hubble and space station. You don't have rocket engines, enough fuel big enough to do that. But what you said with CubeSats, if there's enough close by, you could then go, let's tow this car and go fuel this one. You can do that much easier. And you might have a CubeSat servicer that it's at itself as a CubeSat that services multiple CubeSats. What we're trying to do, the other place where this comes in handy is where this satellite is what's called the A-train. There's a lot of Earth science satellites right after one another orbiting the poles, so it's much easier to get those. The other place is all the communication satellites are in geostationary orbit above the equator. There you can fuel this one, very easily move over and fuel that one. So CubeSat's a very good example where you would eventually do that. Because if you had 100 CubeSats, you might want to keep them going longer by servicing them or replacing instruments as the missions grew. The problem with CubeSats is they're designed for like 2 weeks or a month. I think once they start to get into years, then it makes sense to do that. So what we do here is try everything I just set out, and what we're trying to figure out, if you see in the picture here, you see different font colors, different colors of tools. The walls are black, so we can shut the lights out so we can simulate on-orbit lighting, because it'll be, when we're servicing Landsat, it'll be dark, and we have lights on the deck here, lights on the robot to see what we're working on. So it matters what color the tool is, or how big the font color is, or all those sorts of, how long is the tool? Is it 12 inches long? Is it 2 inches long? We practice all that here with these robots. But if you look, you see the blue and white robot doesn't look like, if you know space robots, it's not a space robot. The reason is space robots are very, very expensive. Like anywhere from like a cheap robot is like $10 million. The Cadillac is like $100 million, maybe $200 million, depending on if it's new design. So I can't buy a lot of those. So you all, as taxpayers, myself, I couldn't justify buying a bunch. I'd love to do it, but can't afford it. These robots are much, much less expensive. So I can buy a lot of these and practice and basically use the same software that drives this flight robot to drive the, because all I really care about when I'm servicing this is where's the end of the robot. I don't really care where the elbow is. I do a little bit, doesn't hit something, but I really care when I cut that tape, do I go this way, how do I go? So I can have this robot tricked by using software to have it follow the same motion and figure out what sort of software I need to go do that. So we use these robots to do that. The other bad thing with flight robots is they also are designed, and there's an example here. This is a full-scale model of what the flight robot would look like. They're tend to design only to be, as a good engineer, you design something only to be to meet the requirements for where it's going to be, right? So this is only meant to be controlled in space, so I don't have really big motors that lift against gravity. And if I do that, if I launch this satellite up there with robot arms on it, it's less tools, less fuel I can launch. So these tend to be very wimpy. They can't lift themselves against gravity. So I either have to have really weird offload schemes, which gets challenging, or I have to drop stuff in the water, which gets very challenging. So these robots tend to be beefy, and what I can do is this tool drive you see at the end is not a commercial tool drive. You can't buy this robot with that on the end. This is the tool drive that goes into the flight arm. So I use this robot to move the end of the tool and tool drive the same way the flight robot or the engineering robot would move it to do the task, and that's how I practice here. So the good thing with these, they're very plentiful. In fact, anyone have an IKEA bookcase at home? If you do, IKEA is using robots now to assemble bookcases. And if you do have a bookcase and assemble robotically, this exact model robot is what IKEA uses to assemble bookcases. So I can buy, the good news is I can buy one of these, I can buy a lot of these, but when I get this robot, I unpackage it, and I open it up, it comes in assemble bookcase mode. It doesn't come in simulate space robot mode. So all the folks you see here that, unfortunately, are not here because it's Friday, there, all the computers back there where we send all the software, we practice on these, because we have to take that software to make this robot not assemble bookcases, but work on satellites, and we have to program it with a lot of custom software to make it do that. And so that's what we spend all our time in this room, making sure we get all that right. And then we have an engineering version of this arm. We'll practice the same task and say, oh yeah, the arm moved the same way. Because this arm's very, very stiff, right? You go in and touch this thing, you can't move it. You touch a flight robot, there's some give to it. We don't want to trick, for example, stowing a tool, pushing really hard, we push the flight robot and we break something. So we spend a lot of time going back and forth to determine what works, what doesn't, what's similar, what's different. All that's what we do here in practice. And that's all great, but it's only going to get you so far because you're still going to have challenges in space, right? Challenge is very tricky, right? Part of why I love doing this sort of work is you're never quite sure, right? You have to think of everything in practice. So how we're practicing all these tasks, we have an experiment called the Robotic Refueling experiment. If you're ever on Jeopardy, it's another secret, I want half the winnings. If the question is what's the last payload ever launched in the space shuttle program, the answer is a robotic refueling experiment, RM. Basically the size of a washing machine. What we have on the top and the side is things you would see on a satellite. We have one of these, for example, on there, and what we did is use a space station robot, and what's also on the front of the box are tools. We use a robot on space station designed to serve a space station to pull out tools and pretend like you would be serving the satellite to prove the technology. So on the ground we say, oh, it mattered the tool was blue. We do it on robot and say, yeah, it really did matter the tool was blue because when it's dark, you need that. Or yeah, oh, we simulated this on the ground. We really didn't take account the robot arm's going to shake. We need to do that on the ground. We practice all that to very validate and kind of perfect our simulation capability because this isn't space, right? I can turn the walls, turn out the lights, it's still not going to be perfect in space. Maybe it doesn't matter. We don't know that. So we practice on the space station, which has been a great asset to be able to use. So we did a lot of work on our end. So the bonus question, if you're in Jeopardy, and the bonus question is EVAs in the shuttle program, the last payload ever pulled out of the shuttle cargo base also are. It's the last thing the astronauts ever did, which is kind of cool. They worked on space station, they took a pump, it failed, they put it in the shuttle. The last thing they ever did was took RM off the bottom of the shuttle, put it on the Dexter robot on space station Canadians built. When the shuttle left, Dexter installed us and then went to work and simulating space robot stuff. And we use these robots on the ground to practice all that. So what we got experience with was, oh, that was a really good simulation, or that part needed to be changed. We got that experience by doing it in space. So that was practicing all the servicing tasks. Before you get there, I mentioned all the lasers and trying to find the thing. You see some pictures here. We have another payload. So RM was an acronym, Robotic Refueling Experiment. Restores the mission over here is servicing a satellite. It's not an acronym. We just sometimes, at NASA, we don't like acronyms. So restore is just restore. And L is for restore LEO, which is the low Earth orbit where Landsat is. There's also geostationary orbit where communication satellites are. So it could be restore G, restore deep space, restore D, whatever. That's the acronym there. But Raven, if you look behind you, you see this box sitting over there. It's a kind of silver box. This is now on space station. You can see a picture over here on the side. I'll try not to put the laser. Which basically, it's mounted outside station. And if you watch, follow NASA, you know that now the shuttle program's not flying. We have a lot of vehicles that go and replenish the space station. Right, the Russians launch Crew on Soyuz. They launch Progress Crew cargo modules. We have Cygnus that launches from Wallops that sends cargo up, sometimes from Kennedy. We have SpaceX Dragon. So as all those vehicles go up, they're getting data from the space station saying, I'm over here, I'm over here. And Dragon's saying, I'm over here, I'm over here. Okay, we're good, let's go dock. And then the arm reaches out and grabs it. When they do all of that, we have this box sitting on space station, which inside this box is a computer. So a flight-rated computer, because you take a computer or your cell phone or whatever, ain't gonna last very long in space. You need special computers, which tend to be a little slower because they're better technology with keeping them able to control in space with the heat control and all that. And then these openings here are different visible cameras and different lasers and LiDARs, and they basically look at the vehicles. You can see the 3 images here, the different data we get as vehicles fly up. What we do is we practice. So pretend like we were gonna service a vehicle, Cygnus, coming up the station. Can this thing predict where that's flying? And we know where it's flying because we get that data from station, so we can fine-tune the algorithms and all of the stuff on that box there by practicing on space station. So with Raven, which is not an acronym as well, we happen to live near Baltimore, so it may or may not be through the Baltimore. You're gonna get up from me, although maybe someone. But it's kind of looking, right, it's a Raven, it's looking over a station as vehicles approach. So we're not feeding any data back to station, we're not feeding the vehicle data back to SpaceX, we're practicing on our side. How do we hand off between the two, right? You get far away, or you look at the Earth, you can see here, Raven's looking down at the Earth. Well, guess what? Your visible camera is going to see the ocean. It may not see Cygnus because Cygnus may be lost in the clouds. So how do you hand over between LiDARs and lasers? And how's all that work. You can see some pictures here. This is Cygnus at the end of the grapple arm. This is what Raven sees when Cygnus is flying. Well, first when it's grappled, but as it's flying up. You see all this stuff in the background. So how do you not get tricked and think this is the edge of the spacecraft? It's easy for our human eyes to do that, but spacecraft, right? That algorithm is only looking at a camera view, and how does it know what's the Earth, what are clouds, what are roads, what's the end of the spacecraft? And that's what we need to determine here when we're flying from Landsat. Where's the solar array? Where's the edge of the spacecraft? Okay, it's moving that way. Okay, that's how it's moving. I can't get tricked by stuff in the background. So Raven's giving us a great experience of doing that on space station to try all that out in advance of doing things on Restore, which will change then what we fly in Restore to make that more successful. So it's like if you watch the World Series, right? As much as I love the Indians and LA teams, love them go straight to the World Series, they don't, right? You start spring training, then you play the regular season, you play a lot of games, and you get to the playoffs. This is kind of our regular season. We're trying this, well, this is the regular season. All these robots here, and that's kind of like the playoffs, right? Raven and RM, we kind of tried it for real. We're at the big game, right? We're the Super Bowl. And then Restore is the actual World Series of the Super Bowl where we're doing it for real, and we're leading all those up. Because any one of them, you just go straight to doing it for real, you might have forgotten something. If you just do it on the ground, you might get tricked into not doing stuff in space. We try to do all of those and check all that back and forth. So, yep. Question.
What's the biggest fail?
What's that?
What's the biggest fail?
The biggest fail? So I think the biggest two things. One would be during the rendezvous. I mean, the worst that would happen is two spacecraft run into each other, right? We have a computer doesn't calculate the right thing, or is off, it's calibrated the wrong thing, and on the ground, we know it's headed the wrong way, and you have to interject, and it's 4 seconds. So the biggest fail would be is mess something up, and you bang into it. So that's why we practice here to make sure that doesn't happen. We practice on space station, make sure that doesn't happen. The other thing is we more service, so we get through all that, that's all great. The next thing would be we start servicing Landsat, and we can't close the valve, or we can't put fuel back into it, and we leave it in a state where it can't. And it's the same thing you did on Hubble, right? The number one rule in Hubble is don't do any damage, right? No matter what you do, it'd be great if you put science in, but don't do anything where you can't keep doing science on Hubble. So those are the two biggest things. One, you damage the servicer where it can't do work, or you damage Landsat by banging into it, or you do something to it where you can't. Because if I can't get the tape off, it can still be controlled, but if I get all the way in and I cut these wires and I try to put fuel in it, then I can't, finish, then you kind of leave it in a state where it can't finish what it's doing. So those are really two biggest things, and that's what we practice.
Small things, not big things.
What's that?
They seem to be small things, not big things.
Sorry, what?
Small.
Yes.
They seem to be like detail that cause big problems.
Yeah, so it's like a failure of a mechanism. It's one thing we're concerned about is right when you're in that autonomous grapple phase, something resets, right? So the one, like if I'm servicing and my robot's cutting and I lose power, I can wait. I can wait a day, I can wait an hour. But the small thing would be I'm just about ready to grab the ring and the power goes out. What do? Small issue now leads to big issue. Do I back the arm away? So those are the big things we spend a lot of time trying to figure out, the small little things, preventing those. Do I have backup cameras? Do I have backup computer? Those are the sorts of things that we try to design in the system that can lead to those bigger failures. Those are really two biggest ones we're concerned about is really that grapple phase, because there's so much going on. You have the two vehicles so close together. You see this is pretty close to relative. I mean, it's just a little bit further up because it's out of the berthing post, but not too far away. Those are pretty close together, moving very fast. And you get a little error in a prediction of where this thing is, and next thing you know, you're on top of it. So it's just trying to predict all those little things. Any other questions?
So if you can extend the life of the satellite by refueling it, what about do you need instruments that have a longer lifetime as well?
Yes. Yes, and so the good thing is, typically when you build a satellite, you saw like the Mars rovers, right? The original rovers designed for 90 days, have been going for 6 years. So the good news is most satellites tend to, when the fuel runs out, most of the satellites still work because we have so much, in some cases, redundancy, or we do such a great job in engineering that typically instruments keep going, and it's usually the fuel that runs out. Right. Or we don't know when the fuel's going to run out. We guess it's kind of going to be next year, and we have to deorbit it anyway because you don't want to run it dry, and then you can't control it anymore. So in most cases, things are designed well beyond, but yeah, you have to get a point where if it was designed, it may change some of the paradigm and how you design things. Because you always add margin in the design, you might get stuck where it's not impacting data anymore. So it's certainly something different. So I mentioned how we do servicing. The other thing you'll see if you came back in a couple weeks is in the middle area there, you can see this 80-20 frame. This is where we simulate the grapple phase. Because again, if this fence was in orbit and I touched it, right, it's going to float away from me. If I grab it on the ground and I grab it all day, it's not moving from me. I think, oh, this is great, this is easy. I get the space, I touch it, it floats away. What we're simulating here is we'll put our engineering arm on this arch here, and what's going to be on this platform is the back end of Landsat. And not only the back end of Landsat, but right behind the ring, right, this is the ring I mentioned that attaches to the rocket, there's a sensor behind it. So when the robot arm touches that sensor, it senses how hard I touched it, where I touched it. It feeds that data to the computer. The computer calculates as if this thing were 2,000 kilograms and in space, how would I move? And it's really cool to see. It's going to program this robot, which is getting built this week and next week, to move like Landsat would move in space. So I can fully simulate that motion. Because you can do things like in the water. The astronauts train in the water, right? And they do a lot of spacewalks, and that's great. But if I touch something in the water, it floats away, water drag's going to slow it down. So that's not a really good representation. Plus all the lasers and the rendezvous sensors on here don't work well in the water. All it's going to do is reflect all the debris in the water and not the actual satellite. You can practice on a flat floor. In fact, we have one back here. There's a table here, finely polished granite table. Basically, there's air pads in here. We turn the air on. You can see the weights here. Just like you use in the gym, the air pad floats at, so if I go to touch it, the physics are almost correct. Because these robots can simulate things floating away, but it still has gears and it moves. It doesn't move like it really would in space. You probably heard, physics classes and stuff, they have frictionless surfaces and zero friction bearings and all that sort of stuff. That's what we're trying to do here, is that air pad is about as perfect as you can get other than in space. So if I had this thing on and floating, as soon as I touch that thing, it would float like it would float away in space. But guess what? There's no flat floor in space. So I can practice all day grabbing this thing, I get to space, and we've had this happen at NASA about simulation where we grabbed it, we got used to the floor stopping our motion, or providing resistance, we got to space and grabbed it, the same way we did on the ground, and said, wait, that moved away faster than it did on, the air pads here actually provide a little bit of resistance, right? It wasn't quite frictionless, or the moment, right, the tipping over didn't happen because that's on a flat floor. And so this motion platform here, which is much like they train fighter pilots, that does a full motion, right? So it really will move and bob just like you really would. The other thing we'll add in is you can see Landsat. You can see this little antenna over here. You can just see off the back there's a solar array. That's only part of it. There's a huge solar array off the back that provides power to the batteries and stuff on orbit or on the vehicle. Those are going to flap, right? They're like when you ride down the road, if you go home tonight and someone pulls up next to you, as they did last night, jams the steering, right? Especially the base, and your windows start shaking. Same thing. All that touching the spacecraft here is going to start exciting these things, and these are going to start flapping. And your spacecraft, when you touch it, is going to move away slowly. It's going to start moving and slow, and as those solar rays flap, we want to practice all that here to make sure. Another Murphy's law is the rate at which those things flex is about the same rate as the arms control. And those control systems playing close to each other is a bad thing. So we're trying to figure out how do you not excite that thing. You ever see the Comancheros Bridge? Right, the wind that blew over the bridge caused the resonance, and then all of a sudden the bridge fell apart. We don't want to grab this thing such that we excite it enough that the solar ray starts exciting, gets more and more excited, all of a sudden it snaps off. So we want to practice all that here, and that's what these robots do. We can simulate that as best we can. And then we go to the flat floor, and we put this robot in flat floor mode, and we touch that and say, okay, that moved the same way. Or like in school, I don't know if you ever did, I certainly did. You knew what the answer was, you got your answer and said, here's the fudge factor I need to add. I need to add this thing, or maybe this term was wrong. And I go back and check my equations. That's how we check our equations here and say, oh, we missed that term. Okay, that's important. It's by testing this stuff on the flat floor. We've also done zero-G planes, which is the closest you can get. There's a place, Zero-G Corporation, you all can actually sign up. I think they fly out of Dulles and out of Las Vegas. $5,000, I think. You get 30 zero-G parabolas, a couple lunar and a couple Martian, 1/3 and 1/6. It'd be great. I'm saving up for at some point. But that's we could simulate floating these. The problem is I can't float a 3,000 kilogram satellite inside an aircraft. So we float a little thing in there, we touch it, we see how it bounces away, then it really is physics. As soon as I touch it, it bounces away, but the plane's not quite perfect, you have air turbulence, it moves around a little bit, but we can play all that back on these platforms, and that's how we check our answers.